So, last class we did the developing flow, but only in a very heuristic fashion, and this time let us look at the fully developed flow, where we said that the flow profile should not change, they look identical. That means you can superpose one on the top of the other with distance. Okay. So, fully developed flow. Okay. Now, in the fully developed flow, I am writing the full fledged Navier-Stokes equation once again. That is where we will start, and we will show that what are the terms that we can actually neglect. So, we will follow the scaling argument here, and we will try to show that how we can get to the revised version. Okay. So, here x scales as L as before, y scales as however d, because the boundary layers have already merged. So, the scale of y is basically d, and u, the scale of u is basically u, that is the, because we saw it is only 1.5 times the maximum velocity. So, it should be, the scale is still the same. Okay. We are not going up by one order. Okay. So, of course, using this from the continuity equation, you have u by L, okay, should be the same as v by d, right. This gives rise to v being equal to u by d by L, okay, where L is much greater than d, correct. So, if that is the case, that when L is much greater than d, okay, you can take v to be almost equal to 0, okay, in this particular case. So, therefore, du by dx is equal to 0, right, okay, du by dx equal to 0. Therefore, this leads to that u is not a function of x anymore, right. You understood the steps. So, we went from the continuity equation, there we showed that v is almost equal to 0, because your L, the length at which you are taking your entrance, this long pipe basically is much greater than d. As a result of that, moment v becomes equal to 0, then by mandate du by dx also has to be equal to 0. So, that would mean that u is not a function of x anymore. Okay. It can be a function of y, it can be a function of any other things, right, but it cannot be a function of x at this particular point, right. So, the momentum equation then becomes very simple, right, because if you look at the momentum equation, the first term vanishes because du by dx is not a function of x anymore, and the second term vanishes because v is equal to 0, right. Okay. So, and if you look at these two terms now in the momentum equation, that is del square u dx square and y square, of course, we know that x scales as L and y scales as d, L being much larger than d. So, then naturally only one component survives, which is this one, this goes to 0, right, because it is L square, right. So, the momentum equation basically, if we write it, vanishes and becomes something like this, dp by dx equal to gamma after all these manipulations, right. Only two terms survives, this one and this one, that is it, right. So, that would be an interesting proposition. When you look at the momentum equation in this particular form, you will find that the flow is obviously moving, but it is a non-accelerating flow, because the convective derivative, which is the convective part, has gone equal to 0. Okay. So, there is no convection, no convective derivative, let us not say convection, no convective derivative or no convective acceleration, that is equal to 0, right. So, the flow is basically happening due to a balance of pressure and viscosity. So, shear is balanced by the pressure, that is what you have, right, shear and pressure, correct, and it is a non-accelerating flow. This part should be very clear that this is only valid in the fully developed regime. Now, Now that we have this particular equation, we do not need boundary layers anymore. I mean, we do not need scaling arguments anymore. We can simply solve the equation from the first principles, right. So, we can write the boundary conditions first. As we write the boundary conditions, so let us take this as x, this as y, this being the axis, right. You can have it in any other way that you want, does not matter, right. So, u is equal to 0 at y equal to plus minus d by 2. The simple reason is that these are walls, so the no slip condition applies, no slip. Okay. The equation also can be integrated, okay, very easily. So, du dy is equal to 1 by mu dp dx into y plus c1, that is the first part of the integral, and then you integrate it once again, 1 over mu dp by dx y square by 2 plus c1 y plus c2. Okay. So, u is equal to 0 at y equal to d by 2, okay, using that. So, u is equal to 0 at y equal to d by 2, then you have 1 by mu dp by dx d square by 8 plus c1 in by d by 2 plus c2 is equal to 0. Okay. So, that is the first one. Okay. So, in this particular case, as you can see, so this is the full expression that you get. Now, u is also equal to 0 at y equal to minus d by 2. Okay. So, in that particular way, you will have 1 over mu dp by dx d square by 8 minus c1 by d by 2 plus c2 is equal to 0. Okay. So, this is the second form that you have. So, there is one more thing that we can apply, that if you look at the velocity profile, it is symmetric, right. It is a symmetric velocity profile because on both sides. So, there has to be an inflection point right at the center, which would mean that your du by dy has to be equal to at y equal to 0 has to be equal to 0 in essence, because the slope has to vanish, right. So, if you look at this from here, you will get your c1 is equal to 0, right, because the slope will vanish, right. And from the other part you can get c2 is equal to minus 1 over mu dp by dx d square by 8, right. So, that will be the other part. So, c1 is equal to 0, c2 is equal to that. Okay. Now, if you so your total u therefore becomes mu dp by dx y square by 2 minus 1 over mu dp by dx d square by 8, or u is equal to minus 1 over 8 mu dp by dx d square 1 minus y by d by 2 square. Okay. Got it? This can be further represented as something like 3 by 2 u (1 minus y by d by 2 square), where this u is written as d square by 12 mu minus dp by dx, right. There is only one pressure gradient, so you can write it instead of partial, you can write it as an ordinary differential as well. Okay. So, as you can see, so therefore, your final expression for u becomes 3 by 2 u minus y by d by 2 square. That is the final expression that you have, where your u is given in that particular functional form, right. Similarly, your f, which is your friction factor, which is tau y wall by rho u square, can be also evaluated. Okay. So, tau wall you can easily evaluate it as mu into du by dy at the wall, okay, and you can divide it by rho u square. So, all these expressions you can find out, okay, find out quite easily. Okay. Now, let us talk about for a round pipe. So, this is for a duct, right, two parallel plates. For a round pipe, the essential expression is still the same, given by 2u into 1 minus r by r naught square in that case, where this u is basically, this is small u by the way, okay, is r naught square by 8 mu into minus dp by dx, right. So, it is a round pipe like this is r naught, which is the radius of the pipe, right. So, it is very similar expression, okay. This time you have to take care of it by using the polar coordinates in this particular case, right. Okay. So, so what did we do? We found that indeed the u, the fundamental takeaway things, u is not a function of x. That was the first point that we took. Second point was that flow is non-accelerating, right. It is a balance between shear and pressure, got it, okay. And there is an exact solution that exists, which is given by this. That would be your fourth point, right. There is an exact solution. That means you know in the fully developed regime. Why did we get away? Because the nonlinear term of the momentum equation got cancelled, because there was no convective derivative to begin with, right. So, taking advantage of that, we were able to now get to this particular situation where the flow velocity actually there was no acceleration term. So, therefore, it offered an exact solution of this particular problem, and that is exactly what we did in here. Okay. But however, few things to note in the developing region, obviously, okay, this is not true. Okay. The flow is accelerating in that particular reference frame. U is not a function of fx only, u is not a function of fx, that statement does not hold water. Okay. And so, therefore, there you have to solve the whole momentum equation, which is what we did in our integral approach, right. Okay. So, you can see over here that once the flow becomes hydrodynamically fully developed, it has got an exact solution. That means in the energy equation, where you have basically ut dt by dy and terms like that, it can be easily applied. This u can now be taken and easily applied over there, right. You do not have to, you can solve it a priori, and you can take that solution and you can apply it in the momentum equation, in the energy equation, provided that you are operating in the fully developed regime of both the cases. That means you are in the hydrodynamically fully developed regime, and of course the temperature or the energy equation is also in the thermally fully developed regime. Okay. So, or it can be the situation, at least the flow has to be hydrodynamically fully developed in order to apply that u and directly place it over here. Okay. So, that is what we have done, and for the round pipe we have seen that we have given an expression for the round pipe as well. Okay. Now, let us see that for temperature, what are the key concepts that one needs to learn, okay, before one takes up this particular problem. Okay. So, let us introduce the concept of mean temperature. In fully developed flow. What do we mean by that? Okay. So, let us take a pipe, round pipe. As I said, round pipe and ducts, they are not very different. Okay. This is of course the center line, this is of course R naught. Theta is obviously in this direction. So, it is theta symmetric. So, this way is x, that way is r. right. Okay. So, there is of course an m dot amount of fluid that is flowing through this particular pipe. There is a net heat transfer that is happening from the wall into the fluid, okay, as it passes through this pipe, and particularly we are interested in this small segment that you see over here, okay. That is what we are most interested in. So, we apply first law, the first law of thermodynamics, okay, over here. So, we say that q double prime, just look at the expression, 2 pi r naught into dx, that is the dx is this elemental section, right. So, this is the total amount of heat that is dumped into that elemental section dx, leading to m dot. Okay. So, the m dot is a mass flux that was coming in. So, the enthalpy of the fluid should have increased in this particular fashion. So, whatever is coming out on the other side should have a little bit more enthalpy than whatever is entering. That is because of the amount of heat that you have actually supplied, right. Okay. Now, for ideal gas, okay, dH is given by Cp dTm, okay, where we are introducing Tm as the mean temperature, and we will see what this is in a second, mean temperature. Okay. So, Tm is basically the bulk temperature of the fluid entering the control volume. This is a control volume. So, the bulk temperature of the fluid that is entering inside into the control volume is given by Tm. Okay. So, all the whatever may be the temperature distribution of the fluid does not matter, it is the average temperature at that particular section. In this particular section, whatever was the average temperature, that is what we have taken, okay. That is your Tm. So, this Tm changes by a little bit because you are dumping more amount of heat, right. There is a fluid which is coming with a mean temperature, you have dumped x calories or joules of heat into the fluid, that naturally the mean temperature will rise a little bit, right. As a result of that, the enthalpy of the fluid also changes by that little bit. So, that enthalpy is given by dH is equal to Cp into dTm. That is, a change in enthalpy is linked to the change in the mean temperature. Okay. So, normally your temperature T would be a function of both x and r, right, because it will be a function and it is theta symmetric. Okay. So, therefore, there is no variation with respect to theta, but with respect to x and r there would be a variation of the temperature, right. So, basically your Tm is the representation of bulk, or in other words average temperature, okay, bulk at the average temperature that accounts for R variation. Understand what is R variation? That means the variation across the radial direction, okay, at fixed x, okay. So, at any fixed x, if you average out over R, the temperature that you are going to get is basically your Tm, okay. So, you have q double prime 2 pi r naught into dx equal to m dot Cp dTm, okay, m dot Cp into dTm, okay. Now, what will be your m dot in this particular case? M dot can be represented by that average axial velocity that you have, that we just derived a few moments earlier. So, this can be written as rho u into A, okay, into Cp into dTm, got it, okay, rho u m Cp into dTm, or in other words you get dTm by dx is given by 2 q double prime divided by r naught rho Cpu, okay. So, this is the average axial velocity, that we already derived earlier, that u, remember that in the velocity profile, if you have forgotten, okay, we already had an expression for u, right. U was 2u to 1 minus r by r naught square. Do you recall that? Okay. So, this is nothing but that average velocity that we are concerned with here. Now, so you can see that for example, even in this particular expression, you know that the u is maximum at the center, right. So, when you actually put r equal to 0, okay, u becomes equal to 2u, that means twice the average velocity, right. Now, this is the average axial velocity, therefore, that is what we have used over there. Remember, we said that we are going to use the momentum equation as much as we can, right. So, this establishes one fundamental relationship between dTm, that means the mean temperature, and the corresponding velocity and the heat flux. This establishes that, and how the mean temperature varies. Now, what is the relationship still between T and Tm? Right, that is what we are going to do before we end this lecture. T and Tm, right. We said that T varies with x and r. Tm is basically takes into account that r variation at fixed x, right. So, there must be a relationship between Tm and x, okay, which we need to establish. Okay. So, that is what we are going to do. So, the relationship between Tm and T over here, if you write this expression once again in the proper form, okay, what you will get is area integral Cp T dA, right. That is a total change if you take into account the temperature. This is the actual temperature, which is a function of both x and r, right. So, you are integrating it across the area, that means across the cross sectional area, okay. So, there you have both u, this u is the fundamental variable, this is not the average, and this T is also the native, the temperature, or the temperature at each point, right. So, based on this expression, also we know that 2 pi r naught dx is given by rho u d Cp dTm, that is also we have just derived. So, therefore, rho u a Cp dTm is equal to d, the area integral rho u Cp T dA. Got it? Just we are just replacing the temperature with that. Okay. So, in other words, or rho u a Cp Tm, basically have to integrate it over the two variables rho u Cp T r dr d theta, right. This is the area, right, or in other words, this will be u pi r naught square. For this is the average area, I mean this is the area, not the average area, okay, into Tm, okay, is equal to 0 to 2 pi 0 to r naught u T r dr d theta, or Tm is equal to pi r naught square by u 2 pi 0 to r naught u T r dr d theta, right. So, this is the expression that you get links Tm with the corresponding T, right, and H, that is the heat transfer coefficient in all these flows, will be given by q double prime into T naught minus Tm, right. Okay. That will be the case for all the cases that we are going to do here. Okay. So, basic point is that we require T in order to calculate Tm, otherwise you cannot calculate H. So, the problem is not gone, you have just transferred the problem to a new variable, which is Tm, which is nothing but it is more like an integral approach, where we have basically integrated out the whole thing, right, okay, in a way that it is understandable, right. And so, we have shown that how the mean bulk temperature is related to the actual temperature, and we have also cast that the heat transfer coefficient perhaps can be written in terms of the mean temperature, only in this particular case. Okay. So, in the next class we will see what is the nature of this Tm, how does it vary, okay, with distance and with different conditions, uniform heat flux or uniform surface temperatures. That we will do in the next class. Thank you.